Hello, good morning everybody. Welcome to the first of the root6 training tasters even. The test comes later, here at BV 2010. We run a training track, well, two training tracks really, one of which is very much the sort of the 101 courses, suitable for runners and trainees and people who are just starting in the industry. And they include a video 101, an audio 101, and a QC 101, so quality control for television delivery. And as well as those courses, we also run courses more aimed at the engineer, the established engineer who's already doing this as his job in a facility. Today's session, HD infrastructure technologies, which I think has been wrongly credited as HD formats in the guide, but today we're going to talk all about HD infrastructure technologies and principally developments in data rates over the last few years. So we're going to talk about 10 gigabit Ethernet, very important, well, it's becoming very important, OM3 10 gigabit fiber optic cabling, and we're going to finish up with 3G video, the newest standard of high definition HD SDI 3 gigabit video. Half of this presentation we've given before, so you may be familiar with some of it if you've been to any of these sessions before, but the last half, which is all about 3G, is very new material, and there's a bunch of test results from a lot of work we did over last autumn. So hopefully, if you have an engineering interest, that will capture you. So as I say, talking about copper cable, twisted pair copper cable, coaxial cable, and the newer standards for fiber optic cable, and how these all integrate into a modern television and film facility. Who in this room would consider themselves a television person, either a technical operator or an edit assistant or an engineer, something in that line? Who? Can I see some hands? Who's television here? Just a few. What about IT? Does anybody in here consider themselves an IT person? Again, just a few. So I'll show you this next slide. This is a real photograph from a real machine room here in London, actually, and you can see those bays there. It looks like a big bale of hay, really, doesn't it? You know, just cabling gone crazy. And if you look towards the back of the room, you can see the video racks, and they're all nice and tidy. And this is the traditional distinction between video facilities and IT facilities. But we love our colleagues in IT anyway. We're moving very much towards much higher data rate models in film and television. HD really is with us. You can watch it on several different platforms at home now, and so consequently all modern commissions and workflows in facilities and studios are very much with an HD endpoint in mind. Film, increasingly, people who handle digital film are moving from 2K to 4K, so again, much higher data rates. And the trend's upwards. Ultra-high definition television will come eventually, and 8K workflows for film will happen as well. Moore's law hasn't run out of steam, and it doesn't seem as if the data requirements of film and television facilities are slowing down anytime soon. So increasingly, systems integrators or in-house engineering departments, the kind of people who plan and build new installations, are looking towards that data backbone first, and maybe the audio-video side of things afterwards. It's becoming a lot more significant. There's a little graph there that shows the data rate of Ethernet against year. You can see when Ethernet first started being used in the early 70s, it was a 2 megabit standard, and today it's a 10 gigabit standard in some instances, and there are test products working at 100 gigabits. So, the gigabit Ethernet that seemed very clever 10 years ago is now looking quite shabby. Changes in storage. Large proprietary SANs that costs hundreds of thousands of pounds are really being replaced by more modest commodity-based storage, and TCP/IP-based storage systems for editing are becoming a lot more common as well. So you can see that the move is from very proprietary fiber-based storage systems to Ethernet-based storage systems that look very much like what you might have at home or in your small office. And facilities are beginning to recognise this, the fact that their network infrastructure, their data infrastructure, is becoming central to their business. The thing about a network-based facility is that they're a lot more flexible. They have a lot more options when it comes to deploying storage and deploying editing workstations and such things. And facilities that are recabling now are looking much more towards the most contemporary standards, which are Cat7 cable, which will currently work at 10 gigabits, but in the future 100 gigabits is on the cards. The big high data rate job that kind of started us off in this arena was the Moving Pitch Company. Very big player, very big film and TV facility on Wardour Street. And in 2007, they completely revamped their network, moving from the Cat5 or Cat6 gigabit type Ethernet to 10 gigabit Ethernet as a backbone technology. And all their fibre infrastructure, which was starting to become a bit aged because they put it in the early part of the noughties, they replaced that with 10 gigabit OM3 fibre. Now 10 gigabits over copper seems outrageous. It doesn't seem possible that you should be able to push that amount of data over a twisted pair copper cable. But you can, and just one little point, that the Germans, the Europeans tend to refer to it as Cat7, and the Americans as Cat6A, an augmented Cat6 standard. But possibly XG10 gig is a more technical, is a more appropriate reference. And although it's only a 600 megahertz cable, by using appropriate channel packing technologies, they're able to push a lot more data over the cable than you think should be possible. As ever, Nyquist still applies, so it really is the cleverness of the channel packing technologies that allow you to push that amount of data over a Cat6A or a Cat7 cable. Now, if there's a little table at the bottom there, you can see how, over the last 15 years, how twisted pair copper cable for data has progressed. When we first started deploying structured cabling systems in the early 90s, Cat5 was the flavour. I mean, you may remember Cat3, but Cat5 was the cable of choice. That has a bandwidth of 20 megahertz and can sustain a data rate of 10 megabits per second. And as you go up through the years, you can see that the data rate essentially increases tenfold every time you go up a generation of cable. But the bandwidth of the cable doesn't go up tenfold, and it just goes to show that the cleverness of the channel packing technology that's employed by Ethernet. The new cable, if you are an engineer or if you're planning an installation, it is a very different kind of cable. And my glamorous assistant Anil has got some samples. Anil, can you pass out the twisted pair copper data cable sets? There should be 4 of them that we can show to the people. Lovely. So if you take a look at these samples of cable that are coming around, there's a few things that I just want you to have a look at. The white cable is this newer style of Cat7 or Cat6A, depending on where you're from, and is a much thicker, much stiffer cable, and employs several techniques that you wouldn't have seen previously in Cat6 or Cat5 cable. You'll notice that the twisted pairs are each wrapped in their own metal foil screen, and then there's an overall metal foil screen. So you often hear this cable referred to as PIMF, pairs in metal foil. The reasons for the differences, well, let me just rewind a tiny bit. The red cable is a Cat5 sample, and the dark purple cable is a Cat6 sample. The big difference between Cat5 and Cat6 was the plastic center former that keeps the pairs separate, and hence in an effort to reduce alien crosstalk between the pairs. That's almost eliminated in Cat7 because of the screening. But the other thing you'll notice is that the difference between Cat5 and Cat6 is the twist ratio of the pairs. It gets a lot more severe on the Cat6 cable. They're twisted a lot more because at the time the thinking was that common mode rejection was the way to cancel out noise on these cables. But by the time you get to Cat7, kind of common mode rejection has gone as far as it can, and Cat7 cable is actually twisted about as much as Cat5 is. The other thing you'll notice about the Cat7 cable, the white cable, you're probably thinking, well, if you've ever crimped off the end of one of these cables, if you're an engineer, how on earth will I put an RJ45 end on that? Well, you don't. There is no crimpable RJ45 end to go on a Cat7 cable. The idea is that you crimp into a plug module that goes into a patch panel, and then to connect to the equipment in question, you use a pre-made patch cord. So there's no playing fast and loose like we always used to with Cat6 and Cat5. It's much more well-defined. Testing is always a big deal. One of the reasons is that manufacturers, generally speaking, will give a very impressive 25-year guarantee if you can show that you've installed and tested their cable system in exactly the way they specified. Tyco, who are the manufacturer we chose when we were doing the big MPC install, their commitment to their customer is such that if you can produce test results to the standard they'd expect, they will warranty that installation for 25 years and make it good should it fail at their own expense. There's some notes there about how you test for 10 gig. As of a year ago, there was still no ratified standard, and so we were using a slightly ad hoc approach. This is the typical results you'd see from a Fluke DTX tester, and that really is the one that everybody expects to see. That's the tester that you'd like to see the results from. And you can see there's an awful lot of information there. Not only a wire map, indicating everything's connected correctly, as you'd get with a mod tap or a pocket tester, the kind of thing that every wireman keeps in his toolbox. But everything that you might be concerned with, insertion loss, skew, resistance, and all the other things like near and crosstalk and remote near and crosstalk and alien crosstalk and all the other things that might give you an indication as to why your data link isn't working as well as it should. That was something that was considered very new and clever about 3 years ago. To be honest, lots of data installers are providing Cat7, Cat6a, whichever you want to call it, and it will be the standard from now on. So if you are commissioning an installation, it's the kind of thing you should be paying attention to. The next technology I wanted to talk about was OM3 fiber, which is the current sort of best kind of multi-mode fiber you can install if you want a future-proof facility and provide 10 gig and beyond standards. As far as we were concerned, it was something of an investment. Not only do we have to invest in new equipment to make off the fiber ends and to train our wiremen and all those kind of things, but we thought that this is definitely the future and it's where we have to be. And a lot of our reasons for getting more and more into fibre optic, bespoke fibre optic cabling, was because we saw the results of other systems integrators' efforts. And typically they'd kind of throw in the pre-made cables that might have come with the equipment, or they'd have some friendly company make them up ludicrously long, very fragile cables which would fail very quickly. And so when we spec a fibre installation, we try and do it with best practice and with an installation that's going to last for many years. So Anil, have you got the other samples there, the fibre optic samples? Could you pass those out? What you'll see here is there's a couple of different grades of fibre. The orange cable is the kind of stuff that you might have seen if you've ever plugged up a storage area network or fibre attached storage, and that's called tight buffered cable or patch cord cable. The other kind is a loose tube cable, and that's typically what you install if you want to do a good job of it. The fibres float inside a mineral oil bath, so be careful, don't get it on your clothes, which is inside that green hose pipe, and that's surrounded by a Kevlar mesh, and then that's all coated in a low smoke, zero halogen jacket. By comparison with the orange tight buffered cable, it's an order of magnitude more robust. Its bend radius, which is always bedeviled fibre, is considerably better because the fibres can slide around inside the oil. And I've seen OB trucks drive over it, and it doesn't damage it. So that's the kind of stuff. If you're planning a fibre installation, that's the kind of cable you should be looking towards. It has a slightly higher installation cost, but the total cost of ownership is considerably less over time. OM3 fibre is a development of previous standards. It's a 50 micron standard, so those little fibres, those little glass fibres you can see sticking out of the green tube, and I think that's an 8-core cable, so you're seeing a little bundle of 8 fibres sticking out of that green tube. Each one of those is a glass 50 millionths of a metre wide, and that's coated in a 125 micron buffer coating, and then that lives inside the mineral oil, which lives inside the green hose pipe, etc. OM3, as mentioned, is 50 micron standard, but it's a glass that's calibrated, manufactured for it's laser optimized glass, whereas previous standards, OM1 and OM2, were optimized for V-cell use, which is the sort of laser LEDs you find in cheaper host bus adapters and network switches and such like. So although there's not any compatibility between OM3 and OM1, contemporary equipment will tolerate both, and so long as you don't have a mixed installation, you'll achieve fantastic data rates with the OM3 cable. And just to kind of finish up the sort of the data side of things, there's a picture that's in kind of as an answer to the first picture I showed you. This is an installation we did a couple of years ago, and this kind of shows you can see the fibre bays on the left there, and then you can see the copper data bays on the right, Cat7 and OM3 fibre, and it shows you what good hard-working wiremen can do. But as I say, we love our brothers in IT. The next thing I wanted to talk to you about was 3G video. This is a new standard which really has come about over the last couple of years, and as a follow-on to HD Cam SR, which was a videotape format Sony launched in 2004. If we rewind to the early 90s, digital video was all about big, thick, twisted pair cables with big 25-way D-type connectors, which would go a few meters, and that was it. So when Sony introduced their Digibeta range of equipment in the early 90s, they recognised that if they were going to sort of dominate the facilities world, they'd have to have an interface that was largely familiar to engineers, could go many tens, if not hundreds of meters, and would work over sort of economical cable systems. So, ever since Digibeta, we've been very used to the serial digital interface, SDI, 270 megabits of video and audio and other metadata over a single coaxial cable that just works very well. And compared to previous digital video standards, is a lot more usable, less ungainly. Fast forward to the late 90s, and Sony launches HD Cam, the first HD range of products, cameras and videotape recorders, and the SDI standard that previously had only worked up to 270 megabits now is extended to work to 1.5 gigabits per second. 6 times the data rate, because there's 6 times the pixels in an HD picture compared to a standard F picture. So HD Cam again uses an HD SDI single BNC connector. You have to be a bit more careful with the cable. You can't just use the same cables as you could for SD. Well, you can, but it doesn't go as far and it's not as reliable. So the industry got used to a distinction between standard definition cable and high definition cable for digital video. As I say, about 5 years ago, Sony introduced HD Cam SR, which everybody assumed would be the last videotape format. It can store RGB pictures at those HD resolutions and frame rates that are suitable for both television and film. And the intention was very much that it would be not only a television mastering format, but also for use in digital film workflows. However, to achieve that, you need 3 gigabits of data off the tape, or out of the back of the machine. It's moderately compressed, so off tape it's about 800 megabits per second. And so the first generation of HD Cam SR VTRs came with 2 BNC connectors for input and output, referred to as dual link. And now you've got twice the cabling requirements and twice the opportunities for things to go wrong, things to be plugged into the wrong hole and problems. And it was always viewed as something of an ungainly standard, something that wasn't really sustainable. But at the time, it was all there was. Until a couple of years ago, maybe 3 years ago, when the HD SDI specification was extended to allow for 3 gigabit video down a single cable. So you've now got 3 gigabits of video, more than 10 times the data rate of SDI when it first started in the 90s, traveling down a single cable, with the advantages that brings, ease of installation, ease of use, and some other technical things like interlink timing discrepancies, all done away with. But you've still got this problem of having to push 3 gigabits per second down a copper cable. When I started out at the BBC in the 80s, 3 gigabits per second was not a data rate anybody could conceive. In fact, 3 gigahertz of analog bandwidth was the kind of thing that came down off a satellite. It's not the kind of thing that went down a cable. So it's amazing that the people who design the interfaces and the electronics for driving this kind of data rate down a cable have achieved it. But they have, and it's with us. And increasingly, new installations are starting to rely on being 3G capable. No doubt, you'll walk around the show, you'll see lots of equipment that is 3G capable. Monitors that have got a 3G input, VTRs, cameras, switches, routers, all 3G capable. And that means they can handle frame rates up to 50 progressive frames per second at 1080 high definition formats. Now, interestingly, when we started thinking about this about a year ago, we couldn't find anybody who'd done any serious testing of what cables were really suitable for 3G. The cable manufacturers were very used to producing cable that worked at 1.5G for high definition video. And you kind of think, just by the physics of it, you double the data rate, you half the performance of the cable. You know, you lose 6 dBs of noise performance and all those things. But nobody would ever kind of put their hand up and say, yes, our cable is certified to this or certified to that. And so we were approached by Bryant Broadcast, who are a big cable supplier, and asked if we could conduct tests on 6 of the most common cables they sell for HD work. Now, Tektronix, who are the sort of the premium brand for signal monitoring equipment and signal generators, they were quite keen to find out the results as well, because they'd been doing a lot of work at Sky and ESPN, where they'd been testing individual cable runs with individual pieces of equipment to see if it would work reliably. But nobody had done a more generic set of tests to say, you know, at this distance the cable works this well, at this distance it works that well, and at this distance it doesn't work at all. And so what we were aiming for was a data set that would allow us, when we're approached to do installations, which is our business, we could say, actually, those 2 rooms are too far apart, we're going to have to pay attention and do it a different way. Or, no, that's fine, you know, that's well within specification. The cable that we had a gut feeling for was a Belden branded cable, 1694 is its part number. And the cable is rated, according to the printed message on the jacket of the cable, to 4.5 gigahertz. And our gut feeling was that was probably going to be the one that would win out, you know, in the tests. Aside from the fact that it's the most expensive cable you can buy for HD video, we thought it would probably be the one that would win through. Now, this display here is the output of a Tektronix WFM 8300 test set, and we're feeding a 3G signal down a 2-meter length of cable, and we're looking as a sort of a starting point as to what the signal looks like when it gets to the other end. The top left tile is what we call an eye pattern. If you're not an engineer, I apologise, because it's going to get a little bit technical now. But the eye pattern is the digital signal overlaid many times on top of itself, so as to give you a feel for how well the receiving piece of equipment is being able to capture that bit stream. So what you're seeing there is you're seeing the rising and falling edges and the tops and the bottoms of the bit stream as it comes off the cable. Now, that might look almost like a sine wave, and not like the kind of square wave that you imagine travels through equipment representing digital ones and zeros. But to be honest, that's pretty good. That's a pretty solid eye pattern. There's no trouble there. And if an engineer was doing a test and he saw that, you know, on his OB truck or in his studio or in his machine room, he'd be happy. That's just fantastic. And then there's the two little green bar markers below give us a couple of different jitter measurements. Now, again, I won't bore you with the technicalities of the way you measure jitter. But jitter is essentially the measurement of how smeary the downfalling edges have become on the signal. So you can see these, they don't look particularly sharp, but actually they're sharp enough to recover the digital data stream and hence the pictures. The Tektronix, rather splendidly, will turn those green bars red when they get into the danger zone and amber when they're approaching it. The bottom right of the test signal generator there shows you the test signal we're using. That's a pathological test signal, which is designed to stress a cable as much as possible. It represents big long runs of zeros and ones on the digital data stream, and is something that's hard for a cable to maintain. And again, I won't go any further with that because you can get really very geeky about that. We did our initial tests using a pathological test signal, which, the eagle-eyed amongst you, if you know your SMPTE specifications, will tell me that that's actually not the way to do tests for overall HD performance using eye diagrams, and that actually real pictures, or colour bars at least, is what's required. We did do the test twice using that method secondly, but the reason we did our most extensive testing using a pathological test signal was because we weren't so much concerned with the damage that gets done to a digital video signal as it goes through a jack field, as it goes through a piece of equipment, as it, all those considerations. Our main concern was what's happening to the signal over long runs of cable. And back in September in our workshop, we had many long runs of cable with ends on them, and lots of testing went on. And I'm very grateful to my colleague Simon Hillman, who tabulated and collected all the data and produced what I think you'll find is a very informative representation of it. The bulk of the tests we did using the correct BNC connectors, the crimp-on connectors at the end, all done by an experienced wireman who is, who wasn't going to be making mistakes in the way the cable was constructed and the way the ends were attached. And then we did try and provoke jitter by mixing connectors with cable, mismatching them a bit. To be honest, we found scant difference between the two. As mentioned, it was the 4.5 gigahertz cable that we found actually in the end was just the best kind of cable for 3G working. Now, Anil, if you've got the very last cable samples, you'll find here, this is a sample of that Belden 1694 4.5 gigahertz cable, which I've just stripped back there so you can see its construction, against a piece of what people refer to as Vision 360, Image 360, or SDO1 cable, very common in the standard definition world. You'll see it in facilities all over the world. But it's the purple cable that's the important stuff here. Now look here, this is a lot to take in, but you can actually see the trends. Going down the left-hand column there, we've got the distance that each length of cable was, cut lengths measured. And then going across the top of the chart, we've got different samples of cable. The first column, the left-handmost column, is that cable you're looking at now, Belden 1694. The second column is a conjufill equivalent. So, although we can never get it from the manufacturer, they claim it's made in the same factory and just badged accordingly. The third column is a Draca cable, which we're not meant to call it Image 1000. It's what engineers have been using for the last 10 years for high definition installations, and we were quite disappointed with how it worked. Actually, it didn't perform as well as we'd expected. And then the last three columns are standard definition cables. We wanted to see, just for the interest, how well they would carry 3G video. So the first one is a Belden 1855, which is colloquially referred to as Vision 360, Image 360, or SDO1. The next column is the conjufill unbranded equivalent, and the final one is another Draca brand, which again is their version of an Image 360 cable. So just taking a look at this chart, you can see at top left the signal's in a very good condition. It's only 1 metre of cable, and all of the cables are able to sustain the 3G data rate over that very short distance. But a 1 metre video cable is of no use when you're installing a TV studio or an outside broadcast truck. And then, as you can see, concentrating on the first column, the Belden 1694, as you run your eye down 10, 20, 30, 40 metres, you can see that eye pattern. So let me go back to, just to refresh you, the eye pattern, which is the top left of the 4-tile display there. If we go back to that one, the eye pattern is gradually degrading as the distance increases, and in fact, as you go along the columns, moving right along the chart, you can see the eye pattern for the lower graded cables degrades a lot quicker, particularly in the case of the standard definition cables, which by the time you get to about 30 metres, the eye pattern, you can barely make it out. But the surprising thing is that how good the electronics in the back of a test signal generator or a VTR are, because even right down to 70 metres, with the very poorest quality cable, we can see that even though the eye pattern is now just a noisy mush, it's still recovering the picture. You can still see the pathological test signal is being recovered. Now, it's hard to see on this screen. On a projector, it's more obvious. But do you remember those two green bar graphs that show our jitter measurement, which is all important in recovering digital video signals? As we go down, and the jitter gets worse, and you can see that by the degradation on the eye pattern. It's getting mushier in that direction, it's getting noisier in that direction. About 50 or 60 meters at the very best quality cable, our Tektronix is starting to warn us with the red indicator, which if you look hard you can see. It's starting to warn us that we really are on the hairy edge of what's an acceptable connection. You know, the red warning crops in at about 20 or 30 meters on the standard definition cables, and it's creeping in, you know, at about 50 meters on the lower quality high def cables, and about 60 or 70 meters on the very high quality high def cables. Now, if we go to the next slide, this is the kind of the rest of that chart, if you will. And in fact, we managed to get right up to 160 meters on the very best quality cable. And even though the Tektronix is warning us that this signal is now almost unrecoverable, amazingly, it's still being able to recover a picture. But we wouldn't recommend anybody relies on that. That's just not reliable at all. So again, the difference between the very best quality high def cable, the Belden 1694, and the more modest quality high def cable, the Image 1000, in real terms is about 40 meters. You can go about 40 meters further reliably for the same error rate using a 4.5 gigahertz cable compared to Image 1000. And then down the side there, you can see the damage that's done to the signals by various things like a BNC barrel, different grades of U-Link, and a BNC patch cord, a Muser patch cord, sorry. And you can see what they do to the signal when you've got a 2 meter length of very high quality cable and then one of those elements introduced into the middle. And it, you know, it's measurable. You know, it pays, if you're putting in a 3G installation, it pays to go with the best quality U-Links you can find and the best quality jack fields, and pay attention to your cable lengths. Just to show that we were conscientious, we redid all our tests using proper pictures, colour bars, and you can see these are the three HD standard cables and how well they work over different lengths. And to be honest, the results are exactly the same as the pathological signal. And we present this really just to show that we're paying attention to the SMPTE regs rather than anything else. As mentioned, the tests were more to do with how far signals could go and not how much damage was done by jack fields and things like that. So our conclusions are that 3G video using coaxial cable goes about 60 meters reliably using the best quality HD cable. And that's when you see the eye pattern starting to close down to 400 millivolts, which is the spec. SD goes about half the distance. Now this for us was counterintuitive because most SD coax has a notional bandwidth plus and minus 6 dBs at 360 megahertz, which is, you know, 3 octaves less than HD coax. And we suspect that the test signal, the test set we were using was actually better at recovering the signal than we'd want it to be. It was doing more hard work than we wanted it to. But the thing that really struck us was the variation between the best and the worst grades of HD cable. So you know, if you are planning a 3G installation, good quality HD cable is what you should be looking at. Again, at 150 meters, we were still able to recover a signal with the Belden cable, and only 120 meters with the Draca, the branded Image 1000. But at these lengths, you know, not only are you looking at a single frame and how much corruption that's suffered, but you're looking at the mean time between failure of video frames and how long will this signal survive before you get a corrupted video frame, and clearly those things are to be avoided. Final thoughts are that in real-world installations, we're not just building TV studios and facilities using Sony and Tektronix equipment. Much as every engineer would like that to be the case, those brands are far too expensive, and you know, economy is a consideration. And if the feel we've got over 10 years for the way regular 1.5 gigabit HD works, there will be an enormous variation in how each manufacturer's equipment works with others. So there are some brands of equipment that will typically drive a 1.5 gigabit signal only 30 meters before it becomes unreliable, whereas a Sony VTR will go up, much further before it becomes unreliable. So even though these tests kind of give us a best case scenario, it does rely on the manufacturers doing the right thing and producing equipment that drives coaxial cable, as well as the big players like Sony and Tektronix. So that's really the meat of my talk today. What's happening with infrastructure and cabling considerations in modern facilities? 10 gigabit Ethernet, data rates ever going upwards. OM3 fiber, a different kind of fiber to previous standards, and 3G video, something you'll see a lot of today, and probably a bit more pertinent to people who are interested in the kind of video solutions you'll find at BVE. So can I open the floor to any questions you might have about what I've told you?